Hi, Robin Beaumont here. I just want to say this video is a quick explanation of how you can carry out a paired samples t-test using the SEM framework, that is the Structural Equation Modeling framework. We'll be using a particular package here called Onyx. You can find out more details, and I published a book which explains SEM in detail and how to use Onyx in detail. On my website as well, there's a particular link to an SEM course I've written, and it explains what software you need to carry out the course. All of it's free. There's additional handout which we're working through at the moment, and the data sets. For this example of the paired t-test, we're going to use a data set that is part of R called the anorexia data set. It consists of 72 subjects that were divided into 3 groups which don't concern us at the moment, but what does concern us is that they had pre-weight and post-weight measurements. Pre-weight, the mean was 82 kilos, and post-weight 85, so on average they gained some weight. The structure of the data frame in R shows that we had 72 observations of these 3 variables, and they're the values. This is the main screen of R. You don't need to worry about it. I just want to get the t-test results and some other values that we can use to compare with the structural equation modeling model we're going to develop. So first of all, we get an overall mean value of our pre and post columns, and it's 83 kilos. So that's the mean value of the pre and post combined. Now we get the data set from the mass package. So we've loaded it. There's the dataset anorexia, and we've asked it to produce a t-test, a paired samples t-test. So here we have a t-value of 2.93, which you'll be familiar with, a p-value of 0.004, a confidence interval, and the mean difference between the 2 groups. We will now close down R, as we don't need it anymore, and we will open up Onyx. Remember, I downloaded Onyx from the website and I put it in a folder. And here we are. I've downloaded the latest version, which is 1.953 now. Click on it and the main window comes up. I don't want it to, there a tip which we can get rid of. I don't want it to take up the whole screen, so I reduce the size of it. Again, it reduces size to ridiculously small amounts. I enlarge it. Now, I just wanted to mention quickly about the previous model we did with the independent samples t-test. The model we created last time for the independent samples t-test in Onyx will appear in a second. There we are. And if you remember, we had 2 groups and they were completely divided. There was no link between the 2 groups. Then we created a model where we estimated the 2 separate means, and then we created a null model where we created a shared mean value and then compared the 2. We're actually going to do something very similar this time, but we're not going to assume them as being independent this time. They're going to be correlated groups. So we close this. Model and create a new model. So we go create new model, create empty model, and there's our model canvas. We collect our data. If you remember, we can't use the R data files, so I converted the R data file to a tab delimited version, which we will now use. You can download the data file from my website as I show you before, and it's called anorexia grp_id.dat. We just drag that to the canvas again. There we are. We want to create a pre-observed variable, a post-weight observed variable. We want to create a constant variable and drag it to that first one, and another constant variable, and drag it to the second one. We want both of these to be free parameters, so they work out on the means. Sometimes it's quite difficult seeing where you're actually clicking with these. So now we have our two samples, pre and post, as we did before in the independent samples t-test. Now the vital difference now is that we create a correlation between the two. So we click on one, press the shift key, then right mouse click and drag to the other. And there's our correlation path. We can use the ends to make it a little more neat, and we wish this to actually be evaluated as well, so make it a free parameter. Also, it'd be nice to see the actual correlation as well as the covariance, so we click on it and choose Customized Path, shows standardized estimates. And if you remember, a standardized covariance is the correlation, 0.33 there. Now, we have one model, and if we look at the summary results for that model, go Show Estimation Summary, we can see it's still chugging through. It's found 61 reliable estimates from 65, and it's still going at the moment. We can see here we've got an estimate for the variance of the pre-rate, variance of the post-weight, estimate of the mean of the pre-weight, estimate of the mean of the post-weight, and we have an estimate for the covariance, the correlation between them as well. Also, interestingly, we have a chi-square value received, which is there from the independence, and that is 8.43. I'll just reduce that window a little bit. What I'm going to do now is create a null model, which is basically with the means set to equal one another. Okay, we'll move that to the corner. You can do. Click on there, then click Edit, Clone Model, and here's our new model, which is identical to that one, and it's already got, as you can see, the data attached to it. And what we're going to do now is remove one of these and just add another constant path there. We want to make them both equal, so we click on there and just call this A. We can call whatever we want, as long as we call the other path the same thing as well. A as well. It seems to have lost that. Sometimes some Intel 2 to get itself organised. So now we have that estimating the overall mean. So now, as in the previous models, we have a null model and a model which shows the observed differences between the groups. We carry out the comparison as we did before. We right mouse click on one and drag to the other, which carries out a likelihood ratio test. We hold our cursor over the bubble and we see what we've got is a -2 log likelihood ratio of 8.25, which produces a p-value of 0.04, which is identical basically to what we had when we carried out the traditional paired samples t-test. We're going to now look at an alternative way of carrying out paired samples t-test, which introduces a new type of variable called a latent variable. We are now going to produce what's called a latent change score model. This approach was developed by Coleman, Pitcher and McArdle in 2013. Now we think here of the post weight variable is being the output from a regression. So the regression has two inputs, two predictors. One is the pre-weight, and another thing is this latent variable. Now, latent variables have got a very bad reputation in the sense that people say, oh, they're not measurable, they can't be evaluated, they don't have a mean, they don't have a variance. That is all rubbish, really. Basically, they're the same as if you come across a concept in mixed models of a random variable, by which I mean you have a fixed effect or random effects, and this is what's known as a random effect. It has a mean value and a variance. We just have to set it. It acts like a bin, as I said before. So what we're going to do is create this model here, and there's some rather unusual aspects to it. First of all, we have a zero variance, and we also have a zero value from the constant. So what we're doing is making that equivalent to zero almost. So and also we have 1 here. So the pre-weight has a partial regression value of 1 to the post-weight, and anything else that really is contributing to the post-weight is via this change score, this latent variable. And because these structural equation models are actually equations, you can equate this to an equation. So here we have the equation relates to this diagram. So the post-weight, which is the output variable from our regression, is equal to 0, which is this, the constant. So we have no intercept in effect. 1 times, which is this, the set beta weight here, the beta, a pre-weight, plus again 1, because this is set to 1 as well, it doesn't show any value, so it means it's 1, times the change score. And again we have this 1 times 0, which in effect is nothing, because 1 times 0 is nothing. So what we end up with is the change score is equal to the post-weight minus the pre-weight. So you can say this change score captures the entire difference between these two variables. So let's create this model and see what we get. So we've just got to change this model quite significantly. First of all, we're going to have a regression line from pre-weight to post-weight, and we won't allow us to do that because we have this covariance. I want to demonstrate that there are certain intelligent things set in this software, which means you can't create a model that's impossible. You can, but it usually spots them. So here we go. There is our predictor to post-weight. We're going to set this to a path value of 1, which is it already. As you can see, it's a fixed parameter. It's not free, and its value is set to 1, so it doesn't show anything there. Right. So that's our first thing. Now we're going to set this to 0, and we want to do that so we don't have any intercept. Alright, so we set that to 0, and we want to set the variance here to 0 as well. So we have our pre-weight now, which we still want to actually be a mean value with a beta of 1 going to the post-weight, which is set to a mean of 0 and a variance of 0 as well. So now we want our latent variable, which is in effect the change score, and we want that to have a correlation, so we should press the shift key. Right, there we are. If we touch the end of the line, we get these guides to allow us to change the curvature, and now we want another regression line set to 1, which it is automatically. We need to just set this so it's actually a free parameter, and it'd be nice to see the standardized estimate as well. We can now see the results for this model. So show estimate summary. We have a chi-square value of 8.25, which is the same as we found before, which is equivalent to the pair t-tests. I would like to concentrate a little bit on this latent variable. If we click on it, right mouse click on it, we can see that it has an estimation option, and the estimation option right at the bottom it says obtain latent missing scores. We're going to click on that. We'll close down this window here, and we'll see now we've got another data window here, and you can see it's got the change score, and this is our values for the latent variable. We can actually look more at these by exporting them into Excel and then comparing various values, which we will do now. Here we are in Excel. We can see we have several columns. The first column is the pre-weights, the second column post-weights, and then the two constants we defined. Then we have our latent change variable with the values along that column, and what I've done next is compared raw pre and post weights, and we can see that the first person lost half a kilo, the second person lost 9 kilos, the third person lost 5 kilos, but then we have a success, someone put on 12 kilos. Now if we take this latent change score, latent score, and then actually subtract that from this constant 82.97, we actually mimic these raw change scores exactly. So where do we get this 82.97? Well, if we go back to our model, we can see here that the 82.97 was the estimated mean to the pre-scores, and you can see here it's the same in the textual output as we'd expect. You might realize that that pre-mean is not the same pre-mean that we had from the observed variable. That is because we have this correlation line that is also affecting the values. We can also graph these two values, and we can see what I've done here is graph the raw latent value, latent variable value there in blue, and I've graphed the post minus pre raw value as well. And you can see, given that one doesn't have this constant value, the mean, they actually mimic one another. They both go up and down at the same rate. Now we return and talk more about the model. Looking back at the actual model in Onyx, you might think, well, why did you draw a correlation line? Because that is saying that we're trying to consider this as being a two-way relationship. There's no direction, but what we're really interested in is this directional relationship. How does the post weight, how is it affected by the pre-weight? And actually in the article by Cohen, Pichot and McArdle, they suggest that we actually do look at a regression line between the pre-scores and this change score. And what happens if you do that, you get a slightly lower p-value, and how you interpret it is a bit difficult, I find. It means a subtle reinterpretation. We're not looking at just the means, we're looking at actually the change score, whether that change score intercept is different. If if we compare it to the pre-weight. So you need to think about the subtle difference between drawing a correlation line which is mimicking the paired samples t-test, or whether you actually do want to consider the difference between the pre and post scores. I'll leave you with that thought.